All right. So let's look at determination of modulus of elasticity from load extension curve. Okay. From load extension curve. So have a look at this. Have a look at this. Most of the questions we are going to be solving is going to be in this form. This is the load. This is the load extension curve. Okay. And this is the load extension curve. So you can see the load, this is the extension. If you want to calculate for the stress, you're going to use this formula to calculate for your stress. That's the load over what area. But in this case, it is what? Original area. Someone is asking why original area. It's because at fracture, we have to uh, use the area of what? Fracture to calculate for what? Uh, that. Okay. We will get to that soon, and you have a look at how that also comes across. So that brings about what? Initial area and what? Final area. That brings about the initial area and then the final area. All right. So as I was saying, this is the limit of proportionality. This is the straight line portion. Okay. This is the elastic region, and also you can see your point. Okay. That is the load being plot against the hot extension. Uh-huh. Uh-huh. If you want to calculate for your elasticity as usual, as usual, as usual. To calculate for your yield stress is equal to, let me say, or it is actually the ratio of load at yield point over the original area. Original area in this case is expressed as A subscript O. Yes. Someone is asking why are we writing stress subscript Y? Is because we are calculating for yield stress. So to denote that we're in yield stress state of mind, that is why we have brought the subscript of Y over there. Okay. Let's look at the ultimate stress. To also calculate for the ultimate stress or maximum stress, this means maximum stress, so don't get confused. Okay, so they wrote just stress and they added maximum to it, a very small one. Don't get confused by that. Exactly. So that is also the maximum load over original. Mhm. Exactly for your percentage elongation, uh, we also have to apply a formula of total extension over the gauge length. What did I say the gauge length is? What did we say the gauge length was?
Originally.
Original length.
Aquadan Aquadaniel, please, what is the meaning of gauge length? Aquadaniel, can you tell us what a gauge length is? All right.
Hello, hello.
Hello.
Okay, that's the original length given in the question.
All right. All right. Thank you very much.
Yes.
So we said elongation is equal to total extension over the gauge length, expressed as a percentage. Okay. That is how you are seeing this over here. Okay. Let's come back to the definition. Percentage elongation. It is defined as the ratio. Ratio means something over something. You understand me? It is defined as the ratio of the final extension. Okay. Or you can say it's a ratio of total extension at rupture to original length expressed as a percentage. Okay. Expressed as a percentage means times 100. So this is also the percentage reduction. Percentage reduction. Percentage reduction. And your percentage reduction is defined as the ratio of maximum change in the cross section to original cross section area. Okay, expressed as a percentage. That is as you are seeing over here. Where the AO is, or let me say, is the original, or A subscript 0 is your original cross sectional area, and A1 is final area at the fracture section. As I was saying, someone can choose to denote it as what? Initial area and what? Final area. Okay, it is all also accepted. All right, all right, all right. So the stress at proportion, at proportional limits to, this is the formula we are going to use. The stress at elastic limit to, this is the formula we are going to adapt. Good. Let's quickly move to solve some one or two few questions and see how best we can all become history. All right. Let's look at this question. The question says that, yeah, hello, Solomon. Yeah, hello, Simon Peter. Please kindly unmute yourself and ask your question.
Hello, sir. Good evening.
Yeah, evening.
Please, I want you, the proof stress, I'm trying to get it, but I'm not getting it. So I want you to shed further light on proof stress and then how we can calculate it and find it on the graph.
All right. All right. Okay, so let's talk about the rupture stress. So the stress at rupture is the stress corresponding to rupture. Mathematically, this can be expressed as what? The load at the breaking point over the original area. All right. Let's look at nominal stress and true stress. Nominal stress and true stress. All right. Direct stress is based on the value obtained by dividing the load by the original cross-sectional area. That is the reason why the value of stress starts dropping after neck is formed in milled steel or any ductile material. As the material is stressed, its cross-sectional area changes. Hence, we should have divided the load by the actual cross-sectional area to get true stress in the material. In the material. If the load is divided by the original area of the cross-sectional area, the stress is known as nominal stress. Note that this stress is lesser at the rupture load than at the maximum load. If we consider true stress, it increases continuously as strain increases, as shown in the figure. All right. So this is it that we are saying. It said if we consider true stresses, it increases continuously as strain increases, as shown. Okay. So the true stresses, you can see that as strain is increasing, they are also increasing. As strain is increasing, they are also increasing. All right. So you can see over here, this is the stress, and then this is the strain. Okay. This is actually our origin over here. And the graph, you can see how the graph has been plotted. So as let me say stress is increasing, or let me say as true stress is increasing, you realize that the strain is also what? Increasing. Okay. And this over here is the nominal stress strain curve. And the breaking ones are the true stress strain curve. The nominal stress and true stresses. The nominal stress is calculated using the formula load over original cross-sectional area. Take note that also the true stress is also calculated using load over the actual cross-sectional area. Load over the actual cross-sectional area. So at this point, I want someone to tell me the difference between the true stress and then the nominal stress. Any volunteer All right, then I'll start mentioning. Okay, Esther. Esther, please kindly unmute yourself and make us history.
Also, please, for the true stress, the stress becomes negative, but for the nominal stress, it's positive. That's what I have to say.
Okay, thank you. Any other person having any other contribution he or she wishes to add? Asari Bernard, kindly make us history. Kindly, Asari Bernard, please
Nominal stress, no.
kindly unmute
Please
yourself.
then, okay. Please, the nominal stress, no, is load over original cross section. Then for the true stress is load over the actual cross section.
All right. So thank you very much. Also, any other person to add up the last thing before we proceed? Hello. All right. So that is what we are saying. That the nominal stress is just actually the load over the original cross-sectional area. Okay. Whilst the true stress is load over actual cross-sectional area. Okay. So just don't mix these two. Especially when you are being asked to provide the answer of this when you are solving mathematically, you should be able to know the right formula to use at the right time. Okay, Nana Ofori, please kindly unmute yourself. You have a question.
Good evening, sir. Sir, please, I want to know the difference between the original cross-sectional area and the actual cross-sectional area.
Hello.
Hello.
Kindly question again.
Yes, I was saying that I want to know the difference between the original cross-sectional area and the actual cross-sectional area.
All right. So the original cross-sectional area is the initial area of a material's cross-section before any deformation or loading occurs. Do you understand me?
Okay.
What did I, can you
Yes.
repeat what I said?
You said the original area is the area of a material before any deformation occurs.
So that is the original cross-sectional area. Okay.
Yes, sir.
That is the original cross-sectional area. And for the actual cross-sectional area, any volunteer to add up to whatever I just said? Hello. Okay. So the actual cross-sectional area is the current area of a material's cross-section. Okay. Taking into account any changes due to deformation, loading, or stress. Okay. So as I was saying,
Okay.
as the lady said initially, so I was just expecting someone should tell me that, oh, it's just the opposite of what I said. And that is all. They are just trying to compare the two. Surely, you know that one will be positive and one will be negative. You understand me? Uh-huh.
Yeah,
Okay. Nana Okori, do you still have any other question to ask or you are okay?
yeah, I'm okay. Thank you.
All right. Thank you too. So I want to Peter. Hello, Peter. Kindly unmute yourself and ask your question.
Yeah,
Yes,
yes,
sir.
sir. Sir, good evening.
Please.
Good evening.
Please, my network wasn't good. The meaning of original processing area, then the actual one, I did not get it.
You know, I said that the original cross-sectional area is the initial area of a material's cross-section before any deformation or loading occurs. If I say you're original, if they say something is original, how do you understand it? The original version of the thing, or original, that is the what factory made. Okay. That was the ever first design of that. Do you understand me? So if I say the original area, you should know that that is what it had. after it was being molded, constructed, or wherever. Okay. But for the actual cross-sectional area, it became the area after deformation took place. Are you now getting me now? So if I ask you to calculate for the true stress, you should know you're supposed. If I ask you to calculate for the nominal stress, you should know you're supposed to use the correct, or let me say, you're supposed to use the original area to calculate for that for me. But in a case whereby I ask you to calculate for the true stress, that is where you're going to use the actual area, okay? Or let me say the area after deformation to calculate for my true stress for me. Coming back to my graph, am I making? Okay, Solomon, please kindly unmute yourself. You are going to be the last person to ask your question, and then we proceed.
So I want to say, can we say change in cross-sectional area, load over change in cross-sectional area, or we are maintaining the actual cross-sectional area?
No.
Since that is the change
No.
that was applied after the fracture.
We have to use the right terms. Okay. If you don't use the
Okay,
right
all
terms,
right.
you find yourself in, in physics, when we say, if we say there was a change, it means difference. Okay. And what you are saying, it means that what you are saying now, it means that like something minus something. Okay. In physics, it is not accepted. Change in something means that something minus something. So what do you want us to subtract from what? Okay, so you can't use it that way. All right, let's talk about the proof stress. Proof stress can be defined as the value of the stress up to which a specified permanent set in percentage of strain remains on unloading when the specimen is unloaded. Also take note that the proof stress, also known as the proof strength, okay, is the stress at which a material, let me say like metal, exhibits a specific amount of plastic deformation, usually 0.1% or 0.2% strain. Yes, it's just a measure of a material's ability to withstand stress without deformation permanently. Okay. Many materials show no well yield stresses when tested in tension or compression. Listen, oh, to specify the yield stress of a material, many times a proof stress value is specified, indicating the percentage strain associated with it. You have to know. Okay. In the case of material which do not show a clear yield point, the yield stress is obtained by offset method. Offset method, by selecting a particular strain value of, let me say, 0.2%, a line is drawn from 0.002 on the strain axis, okay, parallel to the straight line. The straight line part of the stress strain diagram. Mhm. I want to highlight something, okay, for any questions that may follow up. Let me just highlight this down so that when I come back to here, once you read, life becomes much more easier. The stress corresponding to the point on the curve at which this line intersect the curve is taken as the proof stress of the material. The proof stress is taken as yield stress for all practical purpose. We said that what the proof stress is taken as yield stress for all practical purposes. Good. So look at the offset. That is a 0.2% offset. You see, 0.2%. When you say offset, it means that drawing another line parallel to the other. Okay. So if, let me say, I have a line over here. How many of you know how to use the oral card? Who knows how to use the oral card? I hope we all know how to use the AutoCAD.
Yeah, I've used it before.
Okay, so there is a command in there known as offset. If you offset something, you realize that you can either offset front or back, okay, and it's just going to give you a parallel line of that, or let me say shape of whatever you are doing. Okay. Okay. So if this line, I want to offset this. If I offset this, the offset is either going to come to this side or it's either going to come to this side. Okay. So that is just the idea you're trying to put across. It's just going to be parallel exactly. So this line being hot offsetted at 0.20%. Don't be confused. Look at something over here. This is what 0. What 2%. This means that all of this over 100. You see what is happening over here. At the end of the day, if you divide this, what are you going to get? If you want to write this, all of this in decimals, how is it going to become like?
0.002.
So you see that it is still the same as this over here. 0 point, it is still the same as this over here you saw initially. Okay, so it's not anything too strange. Okay, this 0 will move this one over here. This other one also can move it over here. That makes it to become what? 0.002, because there was already a 0 over here already. Okay, so these two people just came to join, and then you realize that that is what we are getting as what? Our 0.002. Don't get confused. Okay, as simple as ABC. As simple as ABC. All right, let's look at and this is the determination of proof stress using the offset method. Take it serious. Please take this very, very, very serious. All right. All right. So let's look at our factor of safety. Factor of safety is very, 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 very essential. Okay. So let's look at factor of safety one. In practice, it is not possible for the in practice, it is not possible to design a mechanical component or structural component permitting stressing up to ultimate stress for the following reasons. One, reliability of material may not be 100%. There may be small spot of flaws. Okay. That is why even we human beings sometimes we also make mistakes. Okay, that is how the machines or equipment we do each and every day, they also make mistakes. Okay. So for factor of safety that we are talking about, if I want to compare this to real life, you see a taxi can carry, let me say, 7 people. You can load it to carry 7 people, it will still carry it. Okay, but you realize that if you still carry that 7 people in the taxi, you end up causing damage to the taxi. Do you understand me? So to ensure factor of safety, what are we saying? We say, oh, the taxi is only 5 people should sit in it. In that case, what are we doing? We are ensuring factor of what? Safety. And that is the same thing we are doing in this case. Okay. But in this case, we are not talking about taxi, we are talking about reinforcement. So let me take it all over again. Factor of safety one. In practice, it is not possible to design a mechanical component or structural component permitting stressing up to ultimate stress for the following reason. That is a minimum for pressure and to add so I could do the highest point. No, you have to put in place measures. One, reliability of material may not be 100%. That is, there may be small spot of flaws. Two, the resulting deformation may obstruct the functional performance of the performance. Three, the loads taken by a designer may only be estimated loads. Take note that occasionally there can be overloading, unexpected impact, and temperature loadings may act in the lifetime of the member. Okay. Let's look at the fourth one. There are certain ideal conditions assumed in the analysis, like boundary conditions. Boundary conditions. Good. Actually, ideal conditions will not be available, and therefore, the calculated stress will not be 100% real stresses. Let's look at factor of safety 2. Take note, for factor of safety 2, hence the maximum stress to which any member is designed is much less than the ultimate stress, and the stress is called the working stress. The ratio of ultimate stress to working stress, and the working stress is also known as what? The permissible stress. Is called the factor of safety. It's called the factor of safety. So mathematically, the factor of safety we have been talking about can be calculated using the formula factor of safety is equal to the ultimate stress, that is the maximum stress over what? Working stress or permissible stress. What did we say the working stress is? We said that when we started reading from here, let me quickly highlight this point too. Hence, the maximum stress to which any member is designed is much less than the ultimate stress, and the stress is called working stress. Okay. So the working stress is just the maximum stress to which any member is designed. Okay. To be less than the ultimate stress, and that is it. What is factor of safety? Factor of safety is actually the ratio of the ultimate stress to working stress. Okay. And this one is for actually brittle materials. This one is for brittle materials. But for ductile materials, the formula we are going to use is what? Yield stress over the working stress. Okay. So you should keep this formula also somewhere. Okay. In case of elastic material, since excessive deformation creates problem in the performance of the member, working stress is taken as a factor of safety, or yield stress, or that of a zero point 0.2 proof stress if yield points do not exist. Take note that the factor of safety for various materials depend on their reliability, or let me say typical values taken in practice. 1.85 for steel and also 3 for concrete, or let's say 4 to 6 for timber. Exactly. Please, up to this point, I want to take some one or two few questions before we proceed to analyze our questions. Okay. Yes. Simon Peter, please kindly unmute.
Yeah. Yeah. Okay, so let's say we are finding the working stress. We just have to do change of subject over there using the formula for factor of safety, right?
No, if you want to calculate, you have to be specific. Working stress for which material? For brittle or ductile?
Ductile material.
Okay, so you can now come again. Now you can come again with what you were saying, so that we can all
Okay.
understand what you are saying better.
Okay, sir. So I'm asking if we are to calculate the working stress for ductile material, we
Mhm.
just do change of subjects using the formula for factor of safety, right?
Yes, exactly. So now the formula I'm going to use is working stress for, that is for ductile material. Your working stress is now going to be the yield stress over the factor of safety. You see. Thank you very much. That was a smart move. Thanks for the contribution. Any other person having any other contribution to add up? In 10 minutes time, the link is going to go off, and we may have to continue some other time because of the time. Okay. But for now, let's quickly see how we can wrap up with this and then analyze the question. Okay. Even before the time catches up with us, so that on our next meeting, we are just going to be doing more of calculations. Okay. They are saying a factor of safety for various materials depend on their reliability. If they say some reliability, the intensity at which someone can put his or her hope in you is what we call the reliability. So the factor of safety for various materials depend on typical values taken in practice, and these are values that have been tested Okay, you see, this is 1.85 for steel. For steel, its factor of safety is 1.85. Okay, and concrete has a factor of safety of just 3. For timber, it ranges from what? 4 to 6. Okay, exactly. You can meet some of these questions in your midterm objectives. You have to be able to know the right answer to select because you have been taught. Okay, okay. Please, any other question? Any other question before we proceed? Any other question? Any other question before we proceed? All right. All right. So let's look at example 1. Let's analyze the question. The question says that a tensile test was conducted on a mid-steel bar. The following data was obtained from the test. That is the diameter of the steel bar is equal to 3 centimeters. The gauge length of the bar is 20 centimeters. The load at elastic limit is 20 kilonewtons. And the extension at load of 150 is equal to 0.21 millimeters. Our maximum load was 380 kilonewton. Total extension was 60 millimeters, and the diameter of the rod at fracture was, let's say, 2.25 millimeters. We are still analyzing the question. So now they're asking us to determine the Young modulus. Secondly, determine the stress at elastic limit. Also, we are to determine the maximum stress, and then we are to determine the percentage elongation. The last but not the least, we are supposed to determine the percentage reduction in area. Percentage reduction in area. Okay. All right. So let's quickly move to a fresh sheet and let's see how best we can be able to analyze the question. So we are talking about problem 2.1. So problem 2.1. Problem 2.1. So let's quickly put down our given. We always have to put down our given for marks. Let's always remember to do that. So that our diameter, which is D. So our diameter D is equal to 3 centimeters. D is equal to 3 centimeters, but we said we work in millimeters, so we convert it, which becomes what? 30 millimeters. Which is the same as our diameter. Okay. Then we come to our gauge length, L. Our L was given as 20 centimeters. If we do our convention, it's now going to become 200 millimeters. 200 millimeters. So we said that this is the gauge length. All right. let's quickly pull down our extension. So extension. So this become our extension. And this become our extension. Extension at load of 150 kilonewton. So extension
It's 250. Oh.
extension of load at can you see the question I'm using over here? Look at the question I'm using. 250. Okay. Let's maintain the 250. So extension of load at extension of load at 250 kilonewton is equal to 0.21 millimeters. So let's write 0.21 millimeters. Okay, good. So our maximum load, let's put it down in total extension. Let's quickly put it down. Our maximum load is 380 kilonewton. So the maximum load. They said maximum load. Maximum load. So this is the same as P. Okay. The maximum load. I can even write P, then I put maximum over here. It's the same thing. So our maximum load is equal to 380 kilonewton. And you know what the kilo means. So 380 kilonewton. 380 kilonewton. 380 kilonewton, which is the same as our 380 times 10 exponent 3 times 10 exponent 3 Newton. Exactly. Now our total extension. Our total extension is 60 millimeters. So the total extension